In my previous video on simple harmonic motion, I explained the concept of simple harmonic motion using a pendulum, and I went on to explain it using a spring, and then I gave a good few equations which are really handy in these type of questions. So in this video, I'm going to do a few Leaving Cert questions that have come up in the past. So the first one I'm going to do is the 2003 question 6 part A. So the question was, a particle is moving with simple harmonic motion of speed pi seconds about a fixed point O. The maximum speed of the particle is 8 centimeters per second. Find the amplitude of the motion. That's the first part. And the second part is find the speed of the particle when it is at a distance of 3 centimeters from O. Okay, so first, I'm going to look at the information that they gave me. So they told me the period is pi seconds, so period is denoted with t. So I know t is equal to pi. Period is pi seconds. I know that the maximum speed of the particle is 8 centimeters per second. So the maximum speed, so the maximum velocity, is 8 centimeters per second. And from there, we have the first part which says find the amplitude of the motion. So to find the amplitude of the motion, I'm going to need the SHM formulae, which I actually gave in my previous video. So you need to look back at that if you need some of the formulae. So the one I'm going to use is T is equal to 2 pi over omega. So period is equal to 2 pi over omega. So we know that the period is pi, so pi is equal to 2 pi over omega. We have pi on both sides, so they cancel. This becomes a 1. We cross multiply, so we get omega is equal to 2. And the units for omega, which is angular velocity, is radians per second. So we have radians per second. So now that we have omega, we still need to find the amplitude. And the next formula I'm going to use is Vmax is equal to omega A. We were given in the question that the maximum velocity is 8 meters per second. Here, we just figured out omega is 2. And now we need to find the amplitude. So divide both sides by 2. I get 4 is equal to A. And the units are meters. So this was pretty easy, and it's just you needed the formulae. And these aren't even in the table, so the only way around this is having to learn them. So you have to learn t is equal to 2 pi over omega, and maximum velocity is equal to omega A. This formula is really handy actually. T is equal to 2 pi over omega. Every time you're given a period, you can find angular velocity, and whenever you're given angular velocity, you can find period. So this formula is really important. So now we'll go ahead and do the second part of the question. So this was part 1 of the question. Now we'll do part 2 of the question. So the second part of the question asks us to find the speed of the particle when it is at a distance of 3 centimeters from O. So for this, we need to use the formula v squared is equal to omega squared times a squared minus x squared. Now this formula is in the tables, and I've never seen an SHM question where you don't have to use this. This always comes up. So this is how you're going to do it. You're just going to substitute everything in. We're looking for velocity. We'll find the speed. So we're looking for velocity is equal to omega is 2, so 2 squared is 4 So I'll write 2 squared. The amplitude, which we found here, is 4. So 4 squared minus the position squared, x squared. They've told us that it's at a distance 3 centimeters from O. So 3 squared. So you get v squared is equal to 4 times 16 minus 9. So you get v squared is equal to 16 minus 9 is 7. 7 times 4 is 28. So v is equal to square root of 28, which is 2 root 7, and the units are centimeters per second. Now, here's the next question we're going to do. This is 2010 question 6, part B. So, a particle moves with simple harmonic motion of amplitude 0.75 meters. The period of the motion is 4 seconds. Find, part 1, the maximum speed of the particle, and part 2, the time taken by the particle to move from the position of maximum speed to a position at which its speed is half its maximum value. So I encourage you to pause the video and try part 1 on your own. It's almost identical to the last part we did, so it should be fine. So pause the video and then I'll go through the solution with you. Okay, so here's how you do part 1. First, you need to note down all the values that they gave you. So they told you that the period was equal to 4 seconds, and they told you the amplitude was 0.75 meters. So just like last time, to convert from period to angular velocity, we're going to use the formula T is equal to 2 pi over omega. So we know that T is equal to 4, and so we have 4 is equal to 2 pi over omega. Divide both sides by 2, you get 2 is equal to pi over omega. Cross multiply and you get omega is equal to pi over 2 radians per second. So you have omega, and now you have amplitude as well, but what they're looking for is maximum speed. The formula for maximum speed is Vmax is equal to omega A. Now we know that omega is pi over 2 and A is 0.75 meters. So we get Vmax is equal to pi over 2 multiplied by the amplitude, which is 0.75, and the answer that you get is 3 pi over 8 meters per second. So that's the answer for part 1. That's the maximum velocity. Now we're going to go ahead and do part 2 of the question. Find the time taken by the particle to move from the position of maximum speed to a position at which its speed is half its maximum value. So here's what we're going to do. First, I'm going to note down the information that I have. I know that I'm looking at the time when the velocity is half the maximum value because that's what they asked me to do. They're talking about the time when the speed is half of the maximum value. So V is equal to half of Vmax at this point. Now we know omega is equal to pi over 2 radians per second. We know Vmax is 3 pi over 8 meters per second. And we know that the amplitude is equal to 0.75. So from here, I'm going to use the equation v squared is equal to omega squared times a squared minus x squared. This formula is in your tables, and the reason I'm using this one is because I can fill in all the variables except for one. I can't fill in x, so that means I'm looking for x. I can fill in, for v, I can fill in half of Vmax, so half Vmax, which would be 3 pi over 16 to be squared. Now, this is 3 pi over 16 because Vmax is 3 pi over 8, and the velocity we're looking for is half of Vmax. So half of 3 pi over 8 is 3 pi over 16. So what we have here is half of Vmax. We know that omega is pi over 2 radians per second. So that squared would be pi squared over 4. Now we know A is 0.75 meters. That squared would be 9 over 16. Now we don't know what x is, so we're going to leave that as x squared. So if you manipulate this equation, you end up getting x is equal to 3 root 3 over 8. So if you look here, there's only one variable in this, which is x. So all you have here is a bit of algebra. So you're going to square 3 pi over 16. You're going to divide both sides by pi squared over 4. Then you're going to minus this side of the equation with 9 over 16. And you're going to divide both sides by minus 1. Then you're going to square root both sides to get x is equal to 3 root 3 over 8. But you're not done yet, because what they're actually looking for is find the time. They're looking for the time. So now the next equation you're going to use, so this is the next thing you're going to do. You're going to use the equation x is equal to a sine omega t. Now if you remember back to my previous video in which I showed the equations, this equation, the 4 time equations, this is one of them, are used anytime there's time in the question. Time was mentioned in this question, so this is why we're going to use it. And there were 4 different ones, but the reason I'm using this one is because something is coming from the center and going out towards the extreme point. Because look, it's asking the time taken by the particle to move from the position of maximum speed to a position at which its speed is half the maximum value. So I'll draw this again to show you. You have a pendulum, the 3 parts of a pendulum. You have 2 extreme points, and you have the equilibrium point. This is the equilibrium, and these 2 are the extreme points. So you have B and A. So the pendulum would swing up and down, where it actually stops here and it stops here. At point A and B, the acceleration is maximum, but the velocity is 0. And at the equilibrium point, point E over here, the velocity is maximum. So this is the point at which you have maximum velocity. And this is the point at which acceleration is 0. So the pendulum is swinging back and forth that this is the idea of simple harmonic motion. So they're asking you about the time where the particle goes from the maximum velocity to half of maximum velocity. So it would be going from equilibrium to a point at which it has half of its maximum velocity. So when something is going from their center or equilibrium point out towards the extreme point, you always use the sine equation. And if something was coming from the extreme point going towards the center, you'd use the cos equation. So we're going to fill in the variables here. So we know from here, this part, that x is equal to 3 root 3 over 8 meters. So I'm going to fill that in over here. 3 root 3 over 8 is equal to amplitude, which is 3 over 4. And then sine of omega t. Omega, from the previous part, is pi over 2. And you're going to multiply that by time, which we're looking for, so we don't know that yet. And if you manipulate this a little bit, you'll get sine inverse of root 3 over 2 is equal to pi over 2t. So pi over 2, once again, is the angular velocity omega. And then when you type this into your calculator, sine inverse of root 3 over 2, you end up getting pi over 3. Once again, you have pi over 2 over here and t. So this gives you t is equal to 2 over 3 seconds. On the basis of the two questions that we've just done, you should be able to attempt a lot of the questions that come up on the simple harmonic motion aspect of question 6 in the Leaving Cert applied maths exam. There's just one more thing that they might ask you, which is they might ask you to prove simple harmonic motion is occurring. So, for example, in this question, they say the distance x of a particle from a fixed point O is given by x is equal to a cos omega t plus epsilon, where a, omega, and epsilon are constants. Show that the motion of the particle is simple harmonic. So this equation looks a lot like, well, it is the same equation as the one we use for finding time. It was given in my previous video. But in this case, now that we have to prove that simple harmonic motion is going on, the technique that you use is that you differentiate twice. So you have x is equal to a cos omega t plus epsilon. So if any of you are in 5th year and you haven't done differentiation, I suggest you come back to this after you've done calculus, because this wouldn't make much sense to you if you haven't done calculus. But if you have done calculus, this is really nice. So anytime they ask you to prove simple harmonic motion in question 6, it's really easy because all you have to do is differentiate twice and substitute. So I'll show you what I mean now. It is something that you can just learn off, and they ask it quite often. So I'm going to differentiate this. So I'm going to get dx, and we're going to differentiate with respect to t. So dx dt is equal to minus a sine omega t plus epsilon times omega. So what we did there is we differentiated the trig function cos. So when you differentiate cos, it becomes minus sine. A is a constant, so it stays the same. So cos became minus sine, so stuck a minus out at the front. So I got minus a sine omega t plus epsilon. When you differentiate a trig function, the inside of the function where you have the t or the x, that gets differentiated and put out at the front and multiplied. So omega is being multiplied by this whole expression. But if you look at this, dx dt, that's distance over time. Distance over time is speed. So this is velocity. All this is an expression for velocity. Since we're going to differentiate twice, we're going to get d2x dt2 is equal to minus a sine as a function. When you differentiate it becomes cos. But we're going to have omega squared here as well. So this is going to be cos omega t plus epsilon. So I'll explain where I got this from. You don't differentiate a because it's a constant. Omega was there already as well, so you don't differentiate that. When I differentiated sine omega t plus epsilon, I had to differentiate the inside as well, which was epsilon, and multiply the function by it. So omega was already there. When I got a second omega, I got omega squared. And when you differentiate sine, you get cos. So I got cos omega t plus epsilon. Now, if you remember back to the start, they told us that x is equal to a cos omega t plus epsilon. So they told us that x is equal to a cos omega t plus epsilon. So we can substitute x for any time we see a cos omega t plus epsilon. And all of this, by the way, is acceleration, because we have v over here. We differentiated that, so this is dv dt, which is velocity divided by time, which is acceleration. So all of this is acceleration. So you get a is equal to, we're going to substitute this we're going to substitute x every time we see a cos omega t plus epsilon. So we see a cos omega t plus epsilon, and we have omega squared and a minus to spare. So we get, what we end up getting then is, you get a is equal to, we're going to substitute in x, so we have minus, and then a cos omega t plus epsilon minus x, but we still have omega squared there. We're going to leave that there, omega squared. So we have minus x omega squared. You can also write this as a is equal to minus omega squared x. Now this proves simple harmonic motion, because if you look back at my previous video once again, we had the defining equation of simple harmonic motion, which was a is equal to minus omega squared x. So acceleration is proportional, directly proportional to displacement from the equilibrium, where omega squared is a constant. So this proves SHM. So this proves SHM. This proves SHM because once we differentiated it twice, we went from having an x to having acceleration. And then once we have the expression for acceleration, we substitute x that they originally gave us into the equation to end up with this, to end up back with a is equal to minus omega squared x. Since we got a fundamental equation after doing a lot of processes, valid processes, this proves simple harmonic motion. This equation was true for simple harmonic motion. So thanks for watching my video. If you have any questions, don't hesitate to leave them in the comment section below, and I'll see you next time.